folks, Mr. G here with another educational video. This is the third part of our Earth Science unit and is going to be another one of our interactive lessons where you're going to be pausing throughout to try and answer the questions first before I tell you the answers. So there'll be some reading, pausing of the video, and it's going to be very important you have a blank copy of the notes with you so that you can be filling these out and trying out the questions as we move along. So this is going to be following quite closely with what we talked about last time, where we were talking about our different types of boundaries and what can happen there. We noticed that at our convergent boundaries, we saw things like volcanoes or mountains being formed, but we really didn't have a clear idea exactly how that happens. So what I'd like you to do is read through these first diagrams here on these first pages, and then answer the questions on our third page. So read through these two pages here, and you might even need to look back at our previous lesson, make sure that all of that's fresh in your brain, and then try out the questions starting on this page with what is a volcano. Pause the video and give it a go. All done? All right, let's go over these together. So what is a volcano? This is an opening in the Earth's crust where magma is being released. Very simply. Now a hot spot, this is an area of the asthenosphere where the magma is hotter than other places. And this is actually how we get a number of volcanoes. This hot spot can melt through our lithosphere, creating a volcano. So if our hot spots stay in one place, the tectonic plates didn't move, and you would get one large volcano. So these hot spots are stationary. So if we didn't have tectonic plates, we would just have one giant island or volcano that's being caused. However, since we have these strings of islands, like our Hawaiian islands, this tells us that our lithosphere must be moving on top of our hotspot. And this supports our theory of plate tectonics. So we have both volcanic island arcs as well as continental volcanoes. Let's talk a little bit about the similarities and differences for how these two form. Well, both of these are happening because of subduction zones. So if one plate is a continental plate, then the volcano will form on our land. If both of these plates are oceanic plates, then our volcanic islands will be formed in the middle of the ocean. So what we see is a little bit different depending on whether our plates are coming together continental plus ocean or two oceanic plates. Those are two different situations for how we get continental versus island volcanoes. Now we know lots of people, you maybe even know some people who live or at least visit Hawaii or other places where there are lots of active volcanoes. Why do you think so many people would live in these regions? Well, there are a number of different reasons. One of the things is that actually volcanic ground is very rich in nutrients because it has lots of minerals which plants need to help it grow. So people oftentimes actually grow crops very near the volcanoes, even on the sides of volcanoes that aren't currently active. The other thing to think about is that just because it's dangerous doesn't mean that people want to leave. It's been their home for many generations. There's lots of tradition and culture, shared ancestry, and they don't want to necessarily leave their home, even if it is dangerous. Take a moment right now and read a little bit about how the Rocky Mountains here were formed. So read this page right here, as well as our continental crust collisions. So these are our convergent boundaries where we have two continental crusts colliding. And I would really encourage you to watch this YouTube video here that shows you how this happens, and then answer these two questions. Pause the video, read through it, watch this video, try out the questions. All done? All right, let's go over the answers together. So why does our collision between plates of two continental crusts differ from what happens where oceanic crust collides? Well, when we have two continental crusts, neither is more dense than the other, so we don't get subduction. So when we had our oceanic plus continental, we always got subduction. Here, instead, our crust gets folded and pushed upwards. This is also partially because our crust is a lot thicker here. It's harder for them to subduct because they're so long and tall. So instead, we get sort of this pushing together, we get these faults, and eventually our mountains get formed as they get smushed together. Burgess Shale is one of the most important fossil discoveries in the world. And it shows us that organisms that once lived in ancient seas are found high up in the Canadian Rockies. So again, how would this happen? Can we use plate tectonics to explain? Well, the rock was likely originally part of low-lying areas that were covered in water. But over time, tectonic movement and collisions pushed it up to form large mountains. So it's possible that the rock that we see on top of our mountains right now were once very low, maybe even right on the edge of an oceanic plate, and were covered in water. And then over time, they got pushed upwards to form these mountains. This next section here, we're going to talk about mantle convection currents. So look at this picture, read through this part here, read a little bit about convection, and then I would encourage you to try and answer these questions on this page. In particular, watching these videos would really help you to visualize what's going on here. So maybe even before you start trying some of these questions, you could try and watch these videos. So read through this, try and answer the questions here, maybe watch some of these videos, and finish off all the stuff on this page. Pause the video, be back with you in just a minute. All done? All right, let's take a look at this. So we've got this picture down here of our mantle convection, or just convection, I guess, in this case. So what do you think is the warmer and colder region of our water? Well, we can see it from the color or maybe from our intuition about heating water up. The warmer water is the red at the bottom because it's right next to the flame, whereas our cooler water is the blue at the top because it's the farthest away. So why does our cooler water sink and our warmer water rise? Well, think back to where we talked about density, as well as what happens when things heat up and cool down. We know that thermal expansion, right, when things heat up, they expand, which means they would get less dense. Whereas when they contract and get cold, they get more dense. So our cooler water is more dense because the molecules move closer together. We talked about this in KMT. And since it's more dense, it sinks. That was one of our first lessons from the chemistry unit, right? More dense, sinks down. So we have this cycle where we have something that's very hot and very low density. It rises up, cools down, gets high density, and sinks again. So we get this circular convection. Now, our mantle does convection as well. What parts of our mantle would be where convection occurs? And our hint is that it can only occur in liquids and gases. It would have to be occurring in our asthenosphere. This is the one part of our Earth's layers that is made up of liquid, like our sticky taffy, right? It can move around and shift, and this is where our convection currents occur. Take a moment right now and read through the mantle convection section here as it shows how our mantle convection can cause divergent and convergent plate boundaries, as these circular arcs can cause things to move apart or squish together. And then when you get a chance, write down a few notes and describe what's happening with mantle convection. Pause the video, give it a try for yourself. Do you have a description written down? Okay, well the one that I have here, yours will probably be different and that's not the problem, is that our magma deeper down gets warmed up, so it rises, just like we saw with the pot of water. Now magma at the top cools, so it sinks, again, just like our pot of water. And this creates these circular currents. As one part is rising, cooling, sinking, heating up, we get this circular motion. And we get these circles happening all throughout our mantle. Big circles, small circles, all of these convection currents. Try these next two questions here on this page, as well as you can try out this online quiz using Khan Academy. See how much you understand with plate tectonics. Pause the video, give it a try for yourself. So to help explain why convection currents cause our slab pull and our ridge push forces, all we need to do is look at our diagram here, where we can see our convergent and divergent boundaries. Here we've got a divergent boundary, these ridge push motions, as well as our slab pull, being pulled downwards. So our ridge push occurs where our magma is rising. It pushes the plates apart. That's our divergent boundaries. And our pull happens where the magma is sinking. It pulls our plates down underneath another plate. And this explains our convergent boundaries. Now, do you think this is true or false? The continual formation of new rock on the ocean floor means that Earth must be getting larger, or at least the crust needs to be getting larger. So, do you think this is true or false? Provide two reasons. Well, this is actually going to be false. New rock is formed at mid-ocean ridges, but our older rock gets destroyed at subduction zones. So, this balances out. We talked about this a little bit last time, right? Our new rock is being formed while older rock is getting destroyed. Now, for this next section, here is an identification puzzle exercise. So it's over the next couple of pages here. What I would encourage you to do is pause the video and try these out for yourself. It goes all the way up to number 15 on the last page here. You should be able to answer all of these questions using the prompts in the pictures here. You might have to flip back and forth a little bit. It might take you a little while. But I think this is a really great opportunity to see how much you understand and how much you know. If you took the version that I had printed out, it is all in black and white. So you might need to take a look at the online version to see some of the pictures in color. You should be able to see them okay, but some of them are probably going to be easier when you have them in color versus others. So pause the video right now and see if you can answer all of these questions on your own. If you get stuck on one part, don't worry about it, just keep moving. Once you get to the end and you've tried as many questions and you've done the best job that you can play the video and we'll go over the answers together. All done? Okay, let's go over the answers together. This first map here is going to be really important because it's going to show us all of our different plates and help us answer some of the later questions. So here is a bathymetric image, and it shows the relative depths of the things. So darker colors are deeper, lighter colors are higher up. So what is this image showing? This is showing us a mid-ocean ridge. We can see our ridge in the middle of the ocean, right? This is our magma coming out of our asthenosphere and rising up and forming new rock. So what sort of plate boundary would cause this? We had three types. This happens from a divergent boundary under the ocean. So our plates spread away from each other and the lava flows up into that empty space, creating a ridge. Here's another bathymetric image. Here, we can see a really deep part as well as a very high up part right next to it. So this is clearly something different. So which feature is this showing? This would actually be showing a deep ocean trench. Here we see our really deep trench in the middle of the ocean. So what type of boundary causes this? This would be caused by a convergent boundary underwater. See, this deep trench is where the plate on the right here is being subducted under the plate on the left. So our more dense plate is going under the less dense plate, so the one on the right must be more dense. And this is happening at a convergent boundary. Here we see a feature in Eastern Africa, in particular along this edge right here. What kind of feature is this? This section right in the middle, this large gap, this is a rift. So what sort of boundary would cause this feature? This is going to be another divergent boundary, but this time under land. As our plates spread apart from each other, the land above it just sinks into the hole. So here, as the plates spread apart, we get a gap forming between the two plates, and all of the other land sinks into the hole in between them. Here we've got Iceland up at the top, and here we see a very similar looking geographical feature. This is another example of our rift. What sort of plate boundary? Again, it's divergent plates under land, just like the one we saw above. And what are the names of the tectonic plates that created this geographical feature? We're going to have to go back. This isn't quite large enough. We're going to have to go back to our first one to see which plates. So we can see that this is our Eurasian plate and our North American plate, two really big plates, and this is our boundary right here. So this is the boundary between our North American and Eurasian plates. Here we get another feature that looks quite similar as well. This looks again like a rift, something that would be created by diverging tectonic plates. Do you think this was created by tectonic plates? Maybe why or why not? And use the map at the start of the exercise to help. Well, here we see where Idaho is. So let's take a look back at our map and try and find where Idaho would be on this map. It would be somewhere around here. As we can see, this is very far away from any of our plate boundaries. And what that tells us is that it's probably not a rift. This is in the middle of our North American plate, and there's no divergence going on here. This is likely caused by actually water eroding the rock. We can see a river formed down the middle here, right? And over time, this river, from erosion, would wear away the rocks on the side of it. So this is probably a very, very old river path. Whereas you notice these two rifts here don't have any water going through it. So it can't be erosion in those two cases. Or if it was erosion, the river has long since dried up. Here we can see a number of islands near to Japan called the Ryukyu Islands. And right here along this plate boundary. Would we expect these islands to be volcanic or not? Explain your reasoning, and then describe how you think they're formed. Well, we know that island chains are oftentimes volcanic because they're right at the edge of our tectonic plates. And they are likely formed by one plate subducting under another. We know that this is what happens to cause volcanoes. Two plates, one subducting under the other, and this causes our magma to rise up and create some volcanoes. Here we've got a picture of Mount Garibaldi and Mount Garibaldi Provincial Park right here. This section in green. Here we see we've got a volcano and a mountain range kind of happening at the same time. So what sort of plate boundary would cause this? Well, if it's a volcano, we know it's convergent. And if it's happening where we get mountains and volcanoes on land, this tells us that it needs to be a boundary between oceanic and continental plates. This also makes sense if we think about where this is in our picture. Here we can see, all the way at the start, our North American and Juan de Fuca plate. Our Juan de Fuca is clearly an oceanic plate, it's in the ocean, and our North American is primarily a continental plate. Finally, here we've got some pictures of the Rocky Mountains all the way through the middle here of the continent, kind of cutting between Canada and the US. Unlike our coastal mountains, the Rocky Mountains don't have any volcanoes. They were raised by tectonic plate activities. However, the growth of the southern region of the Rocky Mountains in the United States is a bit of a geological puzzle that geologists are still gathering evidence to explain. Why do you think that this is a bit of a geological puzzle? All of our mountains are very far inland from the North American plate. Our Rocky Mountains are quite far away from any boundary. So it's a little bit strange to see a big mountain range in the middle here, because there's no plate anywhere close by. We wouldn't expect to see a mountain here unless there was a plate boundary, a continental plate boundary that is converging. Now the last part here, we've got this purple circle over on the right-hand side where we have our Indian and Eurasian plate coming together. And we can see that they're coming together because we've got these two arrows showing that the plates are converging. If we have two continental plates that are converging, what do you think we're going to see? We would see mountain ranges. Again, two continental plates converging. They can't subduct, so they have to grow upwards. So take a moment, if you did, to look up this region and what sort of mountains maybe are around here. So what geographic feature exists in the location and what's the name? These are the Himalayas. This is actually where Mount Everest is. That's the end of the video. Thank you so much for engaging with the interactive lesson. Take the moment right now to check on Teams to make sure you finished all of the other homework that's been posted there, check any announcements, and I will see you all in the next video.